Okay, well, happy Friday, and we'll get started here. So today, I'm taking stuff straight from Tidy with our textbook on using the Tidy Models packages. So I'm not introducing any, say, like new models, or I mean maybe kind of in passing, without giving it much discussion here. But here we're going to kind of get into using these packages here. So the data set that we're going to be working with today is the Ames housing data set. So again, this is data taken from Ames, Iowa, where we look at the sale prices of homes. It's about 10 years old or so, and one of the things we've done is we've already transformed the sale price to be with a log function, okay? And then, so that's kind of the first thing we're gonna do. We transform everything, the sales price, to a log of it, and then we do a train test split here, okay? So we just do initial split. This creates a split object, and then from the split object, we can extract the training set. We can also extract the testing set. So we've got Ames train and Ames test. So this, I think we covered this early on. Okay, and there are, if we take a look at the training set, okay, we've got 2,342 rows, 74 columns, and these are just so you can get a sense of what these columns are. We've got a subclass, a zoning levels. These are factors, and then we have these numeric values for kind of the size of the lot, and then we have factors, whether it's the street is gravel or pavement, if there's an alley or not, just different kinds of things. Okay, the year built and year it was remodeled. Okay, a lot of these houses were built in the 70s, it looks like, at least the first few observations. We've got different roof styles, and I don't know. Okay, and then continuing on, again, 74 variables. So there's a whole bunch of these things. Things about the basement, things about the the condition of the central air and stuff like that. Okay, heating quality, I guess, quality check. The total square footage of the house, and the basement square footage, the number of bedrooms and bathrooms and stuff like that. Other kinds of questions about the garage, and then finally a few more things. And then and one thing that the authors did was they got latitude and longitude values, okay, for kind of if you wanted to plot these things. There's more decimal places. It's just in printing it out, it kind of rounds it off to these, I think, these areas here. Okay. All right. So that's just kind of so you get a glance at the variables, and here we'll some of the variables we'll look at is there a relationship between latitude and longitude and things like that. Okay, so I think we showed some of this last time on Wednesday, but what we can do is we can use the functions in the package Parsnip. So again, Tidymodels is a set of packages, and these packages kind of serve different parts of the modeling function, right? And so one of the packages is Parsnip, and that package is used to fit models. And here we're going to just kind of create a linear regression model, right? And so linear regression model is all about just estimating what those linear coefficients are for each of the different x variables. And our standard method in R, we would just use LM we would do, you know, sale price tilde, you know, x variables, and it would go. Okay. There are other engines for linear regression. Okay. And what we mean by an engine is kind of the algorithm or the system that goes about figuring out these coefficients. Okay. LM is powered by least squares, right? It's trying to minimize the sum of squares residuals, and that's what powers LM. There are other engines, okay? So GLMNet uses what's known as lasso or ridge regression, and I'll explain that in a future lecture, okay? What lasso and ridge regression, and there's kind of a hybrid of those things known as elastic net, okay? And we can use a GLMNet, and that doesn't use least squares or sum of squares residuals, but it uses, you know, another criteria where we add a penalty factor for the size of our coefficients and stuff. Okay, there's something called STAN, and that uses Bayesian principles for the calculation of the parameters. And so, you know, this is not a Bayesian stats course. I think you learn a little bit of Bayesian stats in, like, say, 102C. STAN comes from one of the kind of so Bayesian stuff is powered by a lot of kind of like Monte Carlo stuff, okay? And so I don't know if you guys have taken 102C yet or not, but you got, you know, this Monte Carlo stuff, and one of the kind of the founders of Monte Carlo methods was Stanislaw Ulam. I don't forget his name, but basically the package is named after him, okay? We've got other engines, so you have so some of these are kind of packages you may have heard of: PyTorch and TensorFlow, and maybe Apache Spark for like big data. And so PyTorch and TensorFlow are kind of these neural network based things, and you can use those to kind of figure out your coefficients. And so you have Brule, which provides an interface on PyTorch. Again, you know, they like to have, you know, creative things, right? So creme brulee, you know, using the torch, the French word. So anyway, we got Brule and Keras and Spark, and basically you could learn any of these packages, and they all have different syntax and command structures. And what Parsnip does is it makes it easy for us. Okay, we have basically one interface that we use, and that is kind of able to translate instructions for all of these different engines. Okay, and you can kind of click, you know, for linear regression. If I click this, this takes us to the site, and these are the different engines that are available. Okay, the ones that don't have the two are kind of included as far as Parsnip goes. And then if you see this little superscript 2, it means these engines are available, but you would have to use an extension package. And I'll mention what that is. Okay. And so, and basically, if you want to use any of these methods, you just say, okay, well, we want to do linear regression, and then you do set engine, and you can set engine to LM, or set engine to GLM, or set engine to STAN, and this will just kind of change the computational engine for these linear regression models. Okay, now, in order to work with a model and fit the model to data, we have to create a model object. Okay, and so for linear regression, the model object that we start off with will be the linear regression model object. Okay, as we've seen here, linear regression model object, and then we do things to it like set the engine. Okay, other kind of popular model objects that exist, we have, you know, the random forest. We have kind of boosted trees, which uses XGBoost. We've got logistic regression. We've got simple single layer neural networks. We've got naive Bayes. We've got multinomial regression. We've got, you know, there's a whole bunch of these things. Again, if you read the reference, I think they've got kind of, they list them all off here. These are all specific different model objects here. So you've got any of these things. And so, a lot of these things I don't even know. We have Adam regression models, boosted ARIMA regression models, ARIMA regression models, ensembles of Mars models, ensembles of decision trees, et cetera, et cetera, okay? So a lot of these things I'm not even familiar with, okay? And, but Parsnip makes it so easy for you to kind of start using some of these other things. And so if you're not familiar with a model engine, but you can probably look up some documentation and just get an overview of what sets this model type, model objects apart from some of the other model objects, right? Why is this one better or whatever? And Parsnip allows you to start using it without having to learn all of its new syntax, okay? And kind of the list of supported model objects and engines continue to grow and expand as more people publish, do research and publish new models, and the people who are working on Parsnip say, oh, this is a new one, this is gaining popularity, let's start providing some support for it, okay? So so the maintainers of Parsnip are always kind of trying to keep up to date on the data science community and the packages that are being used and popular, and they try to continue to update Parsnip to allow it to kind of interface and interact with that, right? It's kind of like whenever Apple releases a new iPhone, the developers of your favorite apps have to kind of make some tweaks to kind of support these new things, okay? All right, and so anyway, here for linear regression, we're going to just do linear regression, set the engine, and we're going to store it into just this object. We're going to call this the LM model, and this allows us to refer to it back, okay? And this is just one style where I put the name of the object and the arrow here, and then I've kind of put, using the pipes, each kind of command on its own line, right? This is not required. I could have done this all in one line as well, but I have the space on this slide, so I kind of use this style, and this is what our textbook does, and I think it makes it fairly easy to read as well. Okay. Other model objects, such as the random forest, can be used for regression or classification. And again, we'll talk about decision trees and random forests and stuff in a future lecture. And so if you are going to use a model that is able to do both, you need to set the mode, okay? And you can say set mode regression or set mode classification. And that will tell the model that we need to predict numeric values or categorical values. And again, when you as you explore the different kinds of models that are available, it will tell you what modes are available. So a lot of these things are just regression only, but some of these things allow for both regression and classification. Some of these things are classification only, okay? And so, something like linear regression is only going to be good for regression, right? And then logistic regression, which classifies from, either 0 to 1, that's going to be a classification type thing, okay? So so you would set the mode if especially if it's able to do either one of those things. And then sometimes some of the models, you can specify some of the arguments during the specification of the model itself. So for the random forest, one of the arguments you can specify is how many trees you want in the forest, okay? And the minimum number here, the min n here, is just how many, when you create a tree, you form these branches, and these terminal nodes or the leaves need to have, you're going to say, you need to have at least 5 observations. You don't want to overfit so that every single observation gets its own terminal branch or terminal node. So you can say that, the minimum number of observations needs to be 5. And again, the reference documentation is really going to be what you need to be looking at. So as far as random forest goes, you can kind of click this, and this says, okay, these are some of the different engines that are available, and then these are the different arguments that you can provide. Okay, and we've got mtry for the number of predictors that will be sampled in each tree, and then how many trees and the minimum number of data points in a node. Okay, will be min n here. So that's what we have here. Okay, and so once you've created the model object, then you can fit it to your data. Okay, and there's kind of two ways you can fit the data, and one is using the formula fit, and that uses kind of R's formula specification, and you use the tilde to kind of say, the predictor variable, or I'm sorry, the response variable tilde followed by kind of predictor variables separated with plus signs and so on and so forth. You can also use the XY form. The XY form says, okay, Y, which is going to be basically one data frame with one column, okay, or even a vector, I guess, but a single column of values. That's going to be your target values, and the X will be a matrix or data frame of your predictor variables. Okay, and that's kind of the style used for, say, sklearn. You kind of separate your training data into the target values Y and your predictor variables X. Okay, and so if we wanted to do formula fit, so again, we have the linear model already created. Okay, and so this is just linear regression with a LM linear engine, and that's all we do is I'm going to create a model fit object. Okay, the model fit object is the result of running the model through the function fit. Okay, and so here we're going to just call this the linear model formula fit, and on the next page I've got the linear model XY fit. Okay, so the formula fit says, okay, let's predict sale price as a function of longitude and latitude. Okay, now this is a little bit of a silly model. Okay, because if you think about longitude and latitude, you can think of that as like a coordinate grid on for a city, right? So the Earth is round, but if you just look at one city, you can kind of treat that section as just almost like a Euclidean plane, at least within the boundaries of a city. Okay, and then longitude is where you are going from east to west. Okay, and then latitude will be where you are going from north to south. Okay, and so you're just kind of plotting this out. And according to this, if we're having a linear regression model, what we're effectively doing is we're saying we've got this kind of this plane, and we're just kind of angling the plane. And basically, like, one corner of the city has high prices and the other corner has low prices, right? And as you kind of go from one corner, and is it the northwest corner that's expensive, or is it the southeast corner that's expensive? And you're kind of angling this thing, and expensive houses over here, cheap houses over here, right? It's not going to be a great model, but just that's what we're kind of fitting here, right? Now there could be, I guess some cities could be set up that way, right? I don't know, like New York City and Manhattan, you have the uptown, and as you get kind of further away from Manhattan and stuff, things become a little bit less expensive. But overall, it's kind of a little bit silly to imagine the housing prices just being on some kind of plane, right? But anyway, that's kind of what we have here. and this is the formula fit. If we wanted to do the XY fit, we would create our X matrix, and here all I'm taking is my training data, and I'm selecting the columns longitude and latitude. And again, you could select any of these columns. We have 74 columns available, really, and we can just, here I'm just picking 2 of them. And then, I guess 73 predictor variables available. And then the Y, I'm just selecting the column sale price, okay? Pull is very much like select. Pull is used for kind of just extracting out one column, okay? So pull just gets one of these things, okay? And so once we have these data frames for the X and Y, the XY fit is created by taking our model and then feeding it through XY, and then you just specify X equals X and Y equals Y. And you can actually kind of combine this into just one line here, and that's one thing that they've done in the textbook. So in the textbook, they've done LM XY fit XY. X is equal to, train, select longitude, latitude, and Y is train, pull the sale price. So that's one way to do it as well. Okay, and then if you ask, what is this model fit? Okay, what is the object after we fit it? Well, it says, okay, this is a Parsnip model object. It gives us, it shows us the formula it used, and it gives us the coefficients that it's estimated here. And if I ask for the XY fit, we would see the same results as well. Okay. What we can do is if we want to get any of these things, okay, we can extract the fit engine and use R's base functions, such as summary and coefficients, right? So you can use summary to, get the summary table. And then if you want to pull out the coefficients table from that summary table, you can call coefficients. And these are kind of functions in base R. One issue here, okay, is that, here we get a matrix of these things. These values over here, these are row names. They are not, you cannot actually extract these. These are not available to for you to work with. They are row names stored in kind of the attributes of a matrix, okay? And then some of these column names have spaces or symbols, which will basically make it harder for you to kind of extract out using names as a tool. And then, and this thing says t value, and that's fine and all, because when you estimate coefficients here is you end up performing a t-test. But there are some other, in some other summary tables, maybe you're going to find an f ratio or something like that rather than a t. And so depending, basically this column is dependent upon which summary table we're looking at. Okay, the better method, okay, rather than using all of this, the better method is just to use the function tidy. Okay, so you can just do lm form fit and pipe it into tidy. Okay, so rather, and it's much shorter also. Okay, rather than doing extract fit engine summary coef, you can just say tidy, and you're going to get pretty much the exact same results, except this is a tibble, meaning it's a data frame that we can work with rather than a matrix. Okay, so if you look at all of the numbers are all the same. 302.97, and we have negative 303. The values are actually stored there. It's just tibbles format things for easier printing. Okay, and we have 14.4, negative 21. 14.4, negative 21. Again, all the decimals do exist inside this table. They're just formatted down for printing purposes. So anyway, you call tidy on this, and it creates this data frame or a tibble. The terms show up in its own column that we can kind of extract later. We can take this thing and pull the column term, or we can pull the column estimate or something like that. And these columns, this just has the column statistic, and so it's not specifically referencing, you know, the t-test or an f-test or whatever. It's just the statistic. So, you know, whatever test we use, it would be the kind of this name would work here. Okay, and then it also prints out the p-value. Okay, and that's one of the nice functions. This is under the package broom, part of the Tidymodels thing. Broom, kind of like sweeping or kind of for cleanup. It's cleaning up the output into this kind of nice form that we can work with. Okay, let me give you your first view quiz answer for today. First view quiz answer is the letter B. B as in bear. B as in bear. Okay, once you have your model created, you can use it to make predictions. Okay, the predictions, so you're going to take your fit object and you run it through the function predict. Okay, the result is it's always going to be a tibble. All right, so it's going to always be kind of a data frame. It'll never just be a plain vector or something like that. And then the column names of the tibble, one of the goals of Tidymodels was to make the column names predictable, something that you can kind of expect, or the column names make sense. And however many input rows are in your data set, that's how many rows your tibble will have. And that that's important because in some cases, in other certain models, when you run your data set through predict, if you have missing values, it's going to say, okay, well, I'm not going to bother making a prediction for this, right? If latitude was missing for one of the things, we're not going to be able to produce a prediction. And other models would just kind of omit that thing. And so if you have, a total of 300 observations, and 2 of them are missing values, then the output might be a vector of length 298. Okay, and that, and then you can't kind of take that vector of 298 and combine it with your original data frame of 300. Okay, so one thing about Tidymodels is that if you give it something with 300, it will always output another tibble with 300 rows, and you can always kind of sew those together. If anything has a missing value, then the corresponding row in the tibble output will be an NA if it can't figure out a prediction. And that's great. So over here, all we have to do is we just call predict. Okay. So here I'm taking the test data set. Okay. Ames test. So remember, on our very kind of first slides, we did the initial split between training and test. And here I'm just taking the first 5 rows of test. Okay, so I could have just done Ames test square bracket 1:5 comma to get the first 5 rows. Slice as well as a way, kind of the tidy, piped function that just says, all right, let's just get the first 5 rows. Okay. Borrowing, I guess, terminology from Python, where you just kind of slice your arrays or your data frames. Okay, so here we got Ames test small. This is just kind of the first 5 rows from the Ames test data set. And so all you do is you just do predict. We have this model fit object, and we're going to say, okay, make predictions or apply this fitted object onto this new data. And here we get the values. And here the predict column is called .predictions. So these are the predictions that it is making. And what we can do is we can then combine the predictions with the original target values. Okay. So here I'm going to say, all right, take the test data set. Look at the sale price And then let's combine it with basically this output, okay? And so we're going to use this function bind columns, and it's going to bind the dot prediction to the sale price. And so we can compare, okay, the actual value is 5.02, we predicted 5.22. Actual value 5.39, we predicted 5.21. 5.28, we predicted 5.28. So, you know, we did well over here, not so great over here, and so on and so forth, okay? And then, you know, your predict function, there's other things you can do. One is you can get a prediction interval, a 95% prediction interval, which says, okay, because of the variance in my coefficient estimates, I know that when I make a prediction, the true value could be anywhere. And, you know, I'm 95% confident that the true value is going to be between, you know, within this range, your lower and upper bound of your prediction interval. And so here we do that, and we're going to just bind those columns as well. And so we get a prediction lower and a prediction upper bound for this. Okay, so far so good for using all of this. So again, we're continually building up. We started off with a Parsnip model object. We set the engine. Once we had that model object, we ran it through fit. And now that we've run it through fit, we can use it to make predictions. And that's kind of for very simple models. That's your entire process, right? Take your training data, set up some kind of model, fit, you know, make predictions based on that, or not predictions, estimate your coefficients that's fitting your data. And then once you have your coefficients, you can make predictions with it. So again, the reason why we're going through all of this trouble with Tidymodels is that it really, by learning the Tidymodels syntax, we are now opening ourselves up to being able to use a whole bunch of the different packages and a whole bunch of different statistical models and functions that are out there, okay? And even if we don't have time to cover all of those things in this one class, if you feel comfortable with Tidymodels, you can start approaching some of these other things with just, you know, a minimal amount of I guess, of reading, or, you know, trying to really dig into how these things are, right? So here, we'll create a linear regression model, a decision tree model, and a random forest model. And despite these models being different, if you look at the code is very, very similar, okay? So for the linear regression model, I create my model object by saying linear regression, set the engine. I fit it by taking my model object and fitting it. And then I take the test data, and I'm going to basically bind the sale price with the predictions based on this fit object that we just created over here. Okay, look at the next slide. And if you just kind of flip from one code to the next, it's pretty much the same thing, okay? The only thing that changes is how we specify the model. Up here was linear regression. Now it says we're gonna create a decision tree, okay? For a decision tree, there's different engines available. One is rpart, recursive partitioning. And we're gonna say we need it to be a regression model. And then what do we do? Once we have that model object, we run fit, okay? And the fit command, you'll notice, is exactly the same as this fit command. We're using the formula fit, and it's exactly the same. We didn't have to learn a brand new syntax for interacting with this type of decision tree thing, right? And then once we have this model, if we want to make predictions with it, all we have to do is we just run predict tree fit on the test data. And again, you can see this part is exactly the same. There's no change, right? And indeed, it's a different model because we can see that our predictions being made from linear regression are different from the predictions being made with the tree model. Okay? And then same thing. For a random forest, all I have to do is, again, if you look at how the code changes from here to here, the only thing that changes is just, instead of decision tree, now we're doing random forest. You know, these arguments change. okay? The name of the engine that we're using changes, okay? But pretty much this stuff exactly the same, okay? You fit it using the same command. You make predictions using the same command. You just, of course, you change the name of the objects that you're feeding into this, right? And again, I could have kept going with a whole bunch of these different models, but it feels a little premature because I haven't even taught you exactly how random forests work or decision trees or any of those kinds of things work. But again, this is the beauty of Tidymodels, is that you learn the syntax, you learn how this stuff works, and then Parsnip really does all of the work of basically translating what you're writing here into the different actual commands being needed to use for these different packages. And I think, one of the, in the debate between which one's better, R or Python, kind of one of the things that people complain about R is that the landscape of kind of machine learning is very varied. So everybody's just kind of publishing packages, and the way you interact with these packages is quite different. And there's a learning curve if you wanted to learn how to do, whatever this thing is, right? Without Parsnip, if I wanted to, fit, somebody says, oh, let's fit a REMA boosted regression model. I just go, I don't even know what that is, right? And then, and maybe I take the time to learn how to do it, and then I want to actually implement it. Okay, there might be a whole bunch of stuff, right? So it looks like there's a whole bunch of different parameters, but the nice thing is, even though I've never used this and I have no idea, you probably shouldn't use a model if you have no idea how it works, right? But once you, if you look up a paper or something, so I guess this is a REMA plus XG boost or something. Okay, so anyway, we can be confident in how to use it, in that effectively, all I'm going to have to do is just change this thing from random forest to what was it called over here? A REMA boost, okay? And then Parsnip will do all of the heavy lifting of figuring out, okay, what do we need to do? Now, there might be, and there's a whole bunch of arguments that we can kind of specify, so maybe we need to, read through the number of trees and, how to set this up. So, it looks like we're using, this tree-based system here, but that's a nice thing, right? It really kind of cuts down the work, okay? Even still, there's something even that makes it even easier, okay? And this is there's an RStudio add-in for Tidymodels, or Parsnip, I should say. And I just run Parsnip add-in. Now, I ran this on my home computer, and let me see. I might not have the packages. I might not have it in here. Oh, wait. Let me do library Tidymodels. All right, and let's try Parsnip add-in. Okay, so I need to probably install that packages mini UI. Let me see. It's always risky installing something. Okay, so here I'm going to create just a blank R script over here, and let me see if I can for Parsnip add-in. Okay, so over here, if you run this function Parsnip add-in, you can say, okay, I want to do a classification or a regression thing. Okay, so here for regression, we can say, all right, yeah, let's go ahead and do a REMA boost, and let's do I don't know what these things are: boost tree, decision tree, linear regression with Brulee. Okay, and then I just click write my code for me, right? and look at that, right? It does it. Okay, and you know, you laugh, but this is really it just, you know, you just kind of click these things and it does a whole bunch of stuff. Okay, it's too easy. It feels like you're cheating. It feels like you're cheating, because it's like, oh, I thought this was supposed to be hard, but well, you know, there's an initial learning curve. You gotta understand how these things in Tidymodel works. Okay, you get that, you click the buttons, and then you know, it sets these up, and then you know, now that you have these things specified, you run it through fit, you run it through predict, and so on and so forth. Okay, or you know, if you want to know, like, okay, what are all of these parameters? You can click tag the parameters that we have. Okay, and then and you do that, and it lists off all of these different parameters that you want to do. You can leave it as tune, and tune kind of brings up an interface later for tuning these. And but anyway, you again, it feels like it's a little bit cheating in terms of making this you know, a little too easy or something. So, but again, I don't think I need to keep going on about how Tidymodels is super great. Okay. Okay. Now, a lot of these, so again, as I said, there are a bunch of different packages out there that Parsnip and Tidymodels can interact with. Okay. Now, a lot of these things are not loaded right away. When you first install Tidymodels and you load up Parsnip, it kind of just starts off with your base ones. Okay, it's not, you know, like in games you can get like the DLC to kind of expand like additional things and support stuff, and basically Parsnip, you know, it has kind of, you know, there's downloadable content that you can do to expand the support for these things. So, for example, one of the engines available for linear regression is called GEE, Generalized Estimating Equations. Okay. Now, this package, if you try to use this engine right off the bat, it's going to throw an error. It's going to say, error in this engine G is not supported by linear regression, and you can click type in show engines linear regression, and it outputs something, and you find out, okay, G is not one of those things. Okay, if you want to use G, you need to GEE. You got to load this package, the multi-level mod package. Okay, and so if I do that, right? So I've already installed it on my machine, so I'm not going to run it again. But you install that packages, multi-level mod. You load in that library. It gives me an error. I guess I need to update my R. But here I can run linear regression set engine to G, and it no longer produces an error. Okay, linear regression set engine G no longer produces an error. Okay, now how do I know what like I wanted to use this engine? How do I know which package I need to do? Okay, there's a search feature on the kind of reference site. Okay, so you know, as you're reading the documentation, again, the most important thing is you need to learn how to read documentation, right? So let's say you're doing random forest, and let's say you want to use this thing, H2O, okay? All right, so apparently there's some model, some engine for random forests via H2O, okay? So you say, okay, well, I want to use this because this seems cool because I read a paper about it, or I don't know, somebody on some blog said H2O, super great, okay? So how do I do that, right? So you're going to go to Explore Tidymodels, and you search for H2O. Oh, of course. All right, well, maybe, did I mess something up? H2O? All right, I don't know. Random forest H. Is a wrapper for this? Okay, well, I can't find it. All right, so let me see. Is G? Okay, so when I search for G, okay, we see there's this this package multi-level mod here. I don't know why I'm not seeing H2O here. Okay, well that's I'm not sure.
Like putting just the letter H and C.
Yeah, just that might hit too many things, huh? H. That's not helpful. H2. Okay, it doesn't like it. It doesn't like it for whatever reason. Okay. Well, maybe it's just a matter of installing H2O. All right, let's just try this out. Let's just try this out. Okay. Okay, so we'll run so we'll do random forest. So here it says we'll do something's okay. Here, let me stop this here. Okay, so I'm going to do regression, and let's just see if I can do H2O. So we're going to random forest. We'll call this H2O. All right, so if I run this, let's see. Let's see if this throws an error. Okay, so it says H2 is not supported. So I wonder if it's just a matter of just install.packages H2O. I don't even know, I have no idea what I'm doing here with H2O. I don't even know what this is, right? It's like water, but apparently we can do random forest. So it's a good idea always to, search here, right? So we'll go R random forest H2O. Build a random forest H2O. Oh, that's not helpful, but we got H2O.ai. Now that sounds fancy, whatever it is. Okay, H2O, let's see. H2O.ai is focused on bringing AI to business through software. Well, that's a helpful sentence if I've ever read one. Okay, its flagship product is H2O, the leading open source platform. Okay, I didn't want to read a commercial here, but okay, and apparently it handles a whole bunch of stuff. Well, here we are. Build a random forest model, and it's got all kinds of stuff here. So again, Tidymodels translates this for us nicely, but let's just see. Let's see if we can just do this. Oh wait, we'll do library H2O. Okay, well it loaded. I need to update my R. It keeps giving me this warning here. No, it still doesn't like it. See, show engines. All right, well, okay, well that was a bust. I'm sorry. Usually you can do a search and it'll tell you what package needs to be loaded, but we don't have H2O listed here. H2, nope. Okay, well, it's too bad. All right, so no H2O for us now, but basically there's for a lot of the other things you can kind of look up the appropriate package needed to extend our capabilities here. Okay, let's introduce model workflows. Okay, let me give you your second view quiz answer. Second view quiz answer is the letter A. A as in apple. A as an apple. So the next chapter, chapter 8, is about pre-processing your data. Okay, recipes for pre-processing your data. So pre-processing are things like, these are, when you fit a model, or you do something, sometimes it says like center your data or scale your data, right? Scale it so everything has a mean, center and scale your data so you have a mean of 0 and a standard deviation of 1, right? So that's like standardize your variables, or perhaps you wanted to do some kind of predictions, but it says you can't have negative values, right? So what do? You find your your smallest value and you add a constant, so you shift everything up so everything's at least a positive number, or there's a few other things you can take. If you've got you got negative values, you can like exponentiate things or something, right? There's different transformations that are available to you to make sure you don't have negative values and stuff, okay? Or there's just kind of different pre-processing things. Another one is if you have a categorical variable, you need to turn them into dummy variables, okay? And a lot of times the way we approach these is we say, okay, this is pre-processing, and we do all of this, and then we fit our model, okay? Now, sometimes after we fit our model, we realize, you know what, I need to go back and I need to change the way I did some of my pre-processing, okay? And that can, separating the pre-processing from the fitting of the model entirely, keeping those entirely separate might not be the best approach. And so what a workflow does is it says, let's bundle these things together, okay? And so Tidymodels allows us to kind of create these pre-processing recipes, and we can bundle them together with the modeling, okay? And later on there could be some post-processing stuff, but anyway, if you have a recipe and a Parsnip model, you can kind of combine them together into a workflow. And the advantages is you don't have to kind of keep track of different separate objects. The recipe prepping and the model fitting can all be done together in one step by calling fit on the workflow. And if you have kind of tuning parameters, they can kind of, be handled later with tune. Okay. So first, we're going to just start off with a Parsnip model object. Okay. So we're just going to say linear regression set engine to LM. So this is our LM model. And we're going to say, let's add this to a workflow. So here we're going to create a workflow object. So we start off with the blank workflow object, which is just workflow, empty. And then to the workflow, we're going to add a model. And that's it, okay? And now we have a workflow. Now this workflow is very basic. It just says, it's got a linear regression. And so basically the workflow, it lists off, it says we've got the pre-processing, and we've got the model, okay? So this is what our workflow looks like. So right now there's nothing listed under preprocessor, right? It says preprocessor none, model, linear regression, okay? And as far as the model goes, the computational engine is LM. And this is all we've specified, and this is all that exists in our workflow. Okay, well, we could take our linear model workflow, which again currently has nothing in it, and we can say, let's add a formula. Let's add a formula. Okay, and so this is a little bit different, right? So before, when we looked at the linear model way back here, how do we do it? We created our linear model thing, and then we said fit, and we gave it a formula and the data. Okay, so here we're adding a formula to the workflow, but we haven't called fit on it yet. Okay, so now we're going to take our workflow. So we're just taking this current workflow, which is workflow add model, and then we're going to take that workflow and we're going to add a formula. Okay, so we're going to do workflow add a formula, and so now this formula says sale price tilde longitude latitude. Okay, and it's interesting when we ask what does our workflow look like, the formula shows up in our preprocessor. All right, and this is a little bit of a weird idea, but our formula object actually performs pre-processing steps. So I don't know if you recall, like in 101A, if you put in a factor, a categorical variable into your formula, what did R do? R automatically turned that into dummy variables. And you would get things like under your coefficients, and I don't know if I have a good example here, but it would actually take, if you did provided a factor and you fit LM to it, R would automatically kind of turn those into dummy variables. And that was just kind of a smart thing that LM did. But we can think of that as a pre-processing step, okay? But anyway, so the formula shows up here under our preprocessor. And then with our workflow, we can say, okay, well, let's take our workflow and fit it to our data. So we're going to do fit the workflow to the Ames training data, and that's going to be our fitted object. And we can say, okay, well, what is this? Okay, and so now look at our workflow. So here's our workflow before we fit, and this is what it says. And now that we fit it, it tells us this is our workflow. It's already been trained on data. The preprocessor was a formula. The model was linear regression, and this is the values that it fit. Okay, so it produces the results of having fit the workflow to a set of data. And then once we have a trained workflow, we can say, okay, well, go ahead and make predictions. And just like before, it produces a tibble. Okay, and so these are the values that it predicts after fitting there. Okay, so it doesn't seem like things have changed very much, and indeed they have not. But the key step here is we add the formula to the workflow, and it's not part of the fitting step. Okay, we add the formula to the workflow. It's not part of the fitting step, and instead the formula shows up as a preprocessor, which feels a little bit strange. Admittedly. Okay. What you can also do is you can change the formula. You can take your workflow. Okay. So notice LM fit is my trained workflow. I can take my LM fit, even though it's already been trained. I can update the formula. And I can say, you know what, let's just predict sale price based on longitude. So all we're saying now is, you know, the west side of town is either going to be cheap or expensive, and the east side of town is going to be kind of, you know, cheap or expensive. And, you know, as you go from one side of town to the other, you know, your sale price will change. Now, once we've changed the formula, we have to refit. So notice that when I ask, okay, what does this look like? The workflow no longer says trained, okay? It reflects the new formula under preprocessor, right? Preprocessor is the formula, models linear regression, computational engine LM, but it has no more estimates, and it says our preprocessor, this is the formula that we have. Okay, and then if we wanted to, we could fit it to our data again, so on and so forth, okay? Another thing we could do is instead of having a formula, we can just add raw variables to our workflow. Okay, so here, let me start off with we'll start off with kind of our basic workflow. I'm going to just remove the formulas that exist in the workflow. And we could say, you know what, we want to add the variables. What are the variables? The outcome variable is sale price. The predictors I'm going to use will be longitude and latitude. So this is just kind of another way to specify all of these things. So again, we can use the formula. We can also kind of list off raw variable names. And, you know, there's just depending on how you have your data set up and how you want to interact with it, either of these things will work, okay? And so here we can see, okay, well, what's happening? So our preprocessor here now just shows up as variables, and it says, okay, the outcome variable is sale price. The predictors will be longitude and latitude. We can take that and fit it. Okay. Another way is we could take our workflow. Here I'm going to just remove the current predictors in here. We're going to just remove the variables, and I'm going to and you can add variables. And this is part of the tidyverse. And so you have you have these helper functions that allow you to kind of select variables in kind of a different kind of way. So there are, if you've used dplyr, there are some selector functions, helper functions, that says, you know what, I want to select all variables that begin with basement, okay, starts with basement. Or in this case, I want to select all variables that ends with tud, T-U-D, right? So we're going to get longitude and latitude, okay? So you can kind of, there's, let me look up dplyr selection helpers. Is this it? Where are they? Select helpers. Okay. So you have different selection helpers. Starts with, ends with, contains, matches, numeric range 1 of, everything, so on and so forth. And so you can kind of these are different ways to kind of select your variables. And so, you know, if you're comfortable using a regular expression, you can enter a regular expression into there to, you know, if you have a whole bunch of different column names and variable names as well. Okay, and so here with this, my list of variables, okay, for the says, okay, outcome is sale price. Predictors are the variables that end with tud. And if I say, okay, well, go ahead and fit that workflow to the training data, it does. And it says, okay, now here are your coefficients for longitude and latitude. All right, so find all the variables that end with tud, and it does it. Okay. And that's what we have. Okay. With a workflow, there's a convenience function called last fit. And this is just kind of it does it all at once. You've provided a workflow, and you provide it not the training data, but you provide it a split object. Okay, so remember, at the very beginning, we created a split object. The split object is, you know, how we split the training from the test data. Okay, and if you do last fit with a workflow and a split object, what it will do is it will fit the data on the training, and then it will test the data on the test set, and it will go ahead and measure metrics for you. And I think by default it will measure your root mean squared error and your R-squared values and things like that. Okay, and so it says, okay, well, I fit it on this particular split that you gave me, the initial split that we have, and then it provides it returns the results for the predictions and the notes and the metrics, and they're all kind of stored in this tibble. And so, yeah, maybe it's actually worth getting into that. Did it work? All right, so let me try this. Okay, so we have final linear model results. All right, and then let's go ahead and pull. Oh, sorry. Let's pull dot metrics. Okay, and so if we kind of pull that thing, we can get the root mean squared error, or the R squared values. Okay, and you know, were there any notes? None, no notes. Predictions. Okay, so we had 588 values in the test set, and so these are all of the predictions that it made versus the actual sale price. Okay, and so, you know, if I wanted to kind of confirm predictions. How would I do this? All right, so let's predictions is this, and okay, well, anyway, you could extract this and then work with, say, each of these things to get your root mean squared error and stuff. So all of that, last fit is just kind of a convenience function. If you just want to do a kind of a quick verification of how your workflow is performing. But again, the beauty of the workflow, and we'll do, I'll get into this next week, is with workflows, we can start comparing a whole bunch of these different models. We can start comparing a bunch of these different models. Okay, so I'm gonna, when I was planning out the syllabus, I thought some of these chapters would take longer, and I realized, as I was preparing this lecture, I realized, okay, I need to. It's not going to fill out the full thing. So let me go ahead and I'm going to go ahead and get into chapter 8 here. And this is all about the pre-processing using recipes. Okay. Yeah.
Homework, are we also supposed to read chapter 8, or is it just
For the homework, just go ahead and stick with what I've assigned in the homework, and then I think for your next homework, I'll make sure to include more and more stuff. Okay. And yeah, I have to kind of, we're working out of like 2 textbooks here, right? One is Tidymodels to kind of get your hands dirty here, and then the other is Statistical Learning with R, which kind of covers like some of the ideas behind these different models that exist, right? And so I want to make sure we do both. So we'll be going back and forth, and I have to try to kind of create these homework assignments, and I got to finalize your instructions for the group projects and stuff. Okay, so recipes. With recipes, what we're going to do is we are going to create basically a sequence of steps, much like a cooking recipe, but this is a data feature engineering recipe. Right? So we're going to take our raw data, and we're going to treat the columns in our raw data as our ingredients, and we're going to say, take this thing and do it, okay? Okay, and so something like, take this column of data, and, we want to scale it from 0 to 100, right? So that's going to involve like finding the minimum and finding the maximum and taking that difference and, subtracting the minimum from everything, and then dividing everything by the maximum, and then multiplying it by 100, or dividing by that difference between the min and max and stuff, and that's going to scale everything from 0 to 100. That would count as a recipe. Or, for example, with the Ames housing data, right? There's a variety of ways we can take some of the spatial information, such as we can take the neighborhood, which comes with a name, right? This person lives in, around here. We're in Westwood, and not too far away there's Brentwood, and in the other direction you have Century City and Beverly Hills, and there's the Valley, and stuff like that, right? We can have all of these different neighborhoods. We can take the longitude and the latitude. For Ames, we can say, how far is, what's the distance to the university, okay? And in Westwood, proximity to UCLA is a plus, right? So if you're right in that pocket, right along the hill, that those apartments cost more versus like, if you're willing to live south of Wilshire, it might be a tiny bit cheaper, but I mean, everything in Westwood is expensive, right? So, how far do you have to go before things start getting cheaper? And, how do we encode this data, right? So we can use recipes here, right? So we'll look at some of the the variables available. And so we'll look at the neighborhood. We'll look at the, this is the above grade living area, basically the square footage of the home, when the house was built, and the type of building. And so we have like single family residences. There's 1,900 of those, 1,936. We have a 2-family complex and a duplex. And I'm not quite sure what the difference is. A duplex is basically a building where you have like 2 separate entries and 2 separate kitchens, and it's, you know, entirely separated, and you can have one person and one family living on this side and another family living on the other side. There's a shared wall, and so if you knock too hard on the wall, you can hear your neighbors. But you know, that's a thing, duplexes, okay? And then there's also townhomes, and I'm not sure exactly what the difference is between some of these values, but these are, you know, some of the different variables. Okay. Oh, this got cut off, but so if we want this kind of the traditional way, we would write a formula. And we'd say predict sale price based on the neighborhood. Maybe take the square footage and do a log transformation on it. Take the year built, and then also deal with the building type. Okay, and what it will do, what this formula does, okay, with R, and this all happens in base R, is with this, R is going to say, okay, well, I'm going to do a log transformation on the square footage, the greater ground living area, okay? And then things like the neighborhood and the building type, it will convert these into, it recognizes that these are factors, and it's going to convert them into dummy variables. And so when you here, let me see if I can just go ahead and do this. Okay, so we'll do Ames training. Is it just Ames train? Okay. And so let's see. And log. Okay. H2O coming back and hurting me. Okay. Could not find conflict prefer, or declare a preference with conflict prefer. Oh, geez. Okay. This is annoying. All right. So anyway, you know, if I ask LM fit base, okay. All right, and here, let me just do summary on this, so you can see what happens. Okay. So one of the things R will do is look at all of these things that get produced. Just run the summary thing again. Okay. So it's taken the neighborhood, and for each level of the factor, it creates an estimate. Okay. So it's turned everything into dummy variables, and it says when the neighborhood is equal to Somerset, this is the variable. When the neighborhood is equal to Northridge Heights, when the neighborhood is equal to Gilbert, when the neighborhood is equal to Sawyer, these are the estimates that we're getting. Okay. And you know, when the building type is equal to this or this or this, and one of these is considered like a base thing. So one of the factor levels is like when all of these other things are zeros, that will be kind of the variable. But you can see, you know, we get coefficients for the numeric variables, and then we also get coefficients, but for each level of the factor, right? So R takes this, and looking at the formula, it recognizes that neighborhood is a factor, and it's got to kind of convert this into a dummy variable. Yeah, question?
Is there an easy way to see which one's the base one? Because I always do the like process of elimination.
Yeah, that's kind of usually it's if the, let me see. Okay. Ames underscore train. Let's go ahead and do neighborhood. And let's, so 29 levels, North Ames, that usually the first one forms as the base, but let me just see. So in this thing, North Ames is usually the first one. It acts normally is the base one, and so let me see. Of course, I cleared all of this out, and so I think if we look at this, we're not going to see North Ames. We'll see everything else. So College Creek ends up being the first thing, and then everything else, nothing else shows. And then if we compare that in North Ames, College Creek, so yeah. So I think if you look through it, it'll be, you can always just kind of ask, for the factor, the very first level acts as the base, and then everything else will be like, okay, if it's not the base factor level, then it'll be, when this is true, or when this is true, or something like that. Okay. Okay, so the formula. So this is kind of, this is what recipes is trying to do. It's trying to set, a lot of times when we do this, we see this as the fitting step, okay? But what recipes is trying to say is that when you write a formula, you're giving R instructions to do some pre-processing, like turning the neighborhood into dummy variables, turning building type into dummy variables, or in this case, take greater living area and perform a log transformation. And so what we can do, so if you think about the workflow, remember, like way back here, the formula shows up under the preprocessor, which felt weird to us at the time, okay? But what recipes is trying to say is that, that's actually what R is doing. It's doing preprocessing when it's interpreting that formula. And so here what we can do is we can create a simple recipe of basically the same type of thing, okay? So here we're going to create a recipe. The recipe has the formula. This formula, notice here I don't do, under greater living area, I'm not doing a log transformation here, okay? So when you define a recipe with Tidymodels, you kind of start with this formula and then you add steps. So the recipe basically says, these are the variables. These are going to be the ingredients that go into my recipe, the variables that I'm working with. And then with each of these variables, or with some of the variables, take these actions or these steps. So in this case, what we're going to do is we are going to do a log step. Okay, so basically, when it talks about step, don't think of it as like some kind of staircase and we're doing things. These are just actions that we are taking with these variables, okay? And steps basically only exist inside recipes. So, and we're missing the pipe at the end here. But basically we're going to say take greater living area and then take the log of it. And here we say base 10. And then what we want to do is we want to take the variable neighborhood and turn it into dummy variables. And we want to take building type and turn it into dummy variables. Now we could do step dummy neighborhood, step dummy building type, or we could just do step dummy and then we can kind of give it this argument that says search for all nominal or all kind of categorical predictors. So any kind of predictor that's not a number, so something with words or names or something like that, go ahead and turn those into dummy variables. And then if we look at that result, now we have a recipe, okay? and the inputs says, okay, we've got one outcome variable, sale price. As far as the predictor variables, we have 4 of them: neighborhood, greater living area, ground living area, year built, building type. Okay, and then the operations, log transformation on ground living area, dummy variables for all nominal predictors. So the nominal predictors being neighborhood and building type. Okay, and so that's what it lists off. Okay, so the function all nominal predictors captures the names of any predictor columns that are factor or character. So this works with both factor or kind of character variables, which is nice, right? And the advantage of working with recipes is that these, if you needed to do this these steps again for a different model, okay, you can do that. Versus, if you depending on the interface, right? So with LM, we use recipes, or not recipes. We use the formula. We said predict sale price tilde this and this and this, right? But then some of the other packages like GLMNet or something like that, it requires an XY interface or something like that. And again, by kind of separating out the pre-processing step from the formula allows us to prepare our data for the different kinds of models. Okay, if you're only working with LM, sure, use the formula, not an issue. Okay, and if you're only working with models that use the same formula format, then it's not an issue. But a lot of times, if you want to, again, use any of these different models out there, they require your data to come in some kind of cleaned up or pre-processed form. And so the recipe allows us to kind of separate this out into one step to prepare it as part of the recipe, and then we can take the results of that and pipe it into the different models. Okay. So recipes also allow us a broader set of data processing choices rather than just the kind of base formulas that R has. Okay. The syntax can also be very compact, such as, we can use all nominal processors and stuff. And then all of this is stored in kind of a single object rather than, before recipes, what you'd often do is you'd write a script. Okay, if you realized you had to do this kind of similar pre-processing thing for a bunch of different data, you would write a script, and that's fine. But this, again, just makes our life a little bit easier. So what we do here is we're going to take kind of our workflow. We'll remove the old variables, okay, and then we're going to add a recipe, okay. And so our linear model workflow now has the simple aims recipe, along with it still has the linear regression model as part of it, right? So our workflow, our preprocessor is the recipe that we provided, and the model is still the linear regression model. And then the preprocessor, as far as the recipe goes, it says 2 recipe steps. Do a log step and a dummy step. And then the model part, it got cut off here, but it's still the linear regression model. And so this is our workflow. And then with our workflow, we can fit it. And then once we fit the workflow, we can make predictions, okay? And it says prediction from a rank deficient fit may be misleading. And that's indicates, we've got some of our dummy variables, I think, only had one observation, okay? And so when you have only one observation and you're estimating something like that, then you run out of degrees of freedom. So that's what we're getting this warning here. I think some of our neighborhoods only had so we're trying to get estimates of what is the coefficient for these neighborhoods, and it's based on just one observation. So that's why we're and some of them we had so few that just by random chance in the training data we got 0 observations for that particular neighborhood, right? So now we're trying to estimate what's the effect that this neighborhood has, but we have no observations in that neighborhood. So that's why we're getting this this thing. But that's fitting. So you add the recipe to your workflow, and then now you can kind of fit your workflow on your training data. Let me give you your third view quiz answer. Third view quiz answer is the letter C. C as in cat. C as in cat is your third view quiz answer for today. Okay. I didn't feel like typing all of the stuff, and so here I want to just kind of point you to a few places for reading, and we can go through some of this. We've got the time to do it. Okay. These are some of the different recipe steps that we have. Okay. So again, as far as what can you do with a variable, there's a whole bunch of things that you can do. Okay. Right. So one of the things is taking our factors so that they can be represented numerically, which is going to be important, for like regression. Okay. Sometimes we need to kind of fill in, what do we do when we have missing values, right? Do we impute something? Do we fill it in the mean or something? And so we can do that, right? So step unknown can be used to change missing values to a dedicated value. Okay, and if we anticipate that a new factor level might be encountered, we can do step novel. So it says, if our training data has some of these things, but then we encounter a new neighborhood or something, we can use that. Okay, step other. We can use that to kind of, it says, can be used to analyze the frequency of the factor levels in the training set and convert infrequently occurring variables to a catch-all level of other with a threshold that be specified. So, for example, if we look at the neighborhood, we ran into this issue where we didn't have enough observations from these neighborhoods, so that we ran into problems. And so we can just say, let's only look at some of these most important ones, right? So it says we see these two neighborhoods, Landmark and Green Hills neighborhoods, have less than 5 properties in the training data, and in our case, we actually had none of the properties in Landmark, right? So when I ask for summary on the neighborhood, let me shrink my text here. Okay, so when I asked for the summary, we had, I guess none from Hayden Lake. Okay, 1 from Landmark or something. Okay, when I asked for a summary on this data, we're running into problems here. And so what we can do is we can say, turn these variables into other. Okay, so rather than saying we're going to specifically turn this into its own dummy variable, let's turn it into just category other. Okay, and so anything that doesn't kind of fit the other ones, the main variables, we can turn this into another, right? And I feel like that's a common thing that we have to do when we have data with a whole bunch of different categories. It's kind of like, all right, you want to keep track of like, is the color of the car important as far as something goes, right? Do certain colored cars get more tickets than others, more traffic citations than others? And how many colors are there, right? Most of your colors are what? Silver, gray, white, black. That covers like a lot of cars. And then you got red cars and blue cars. And then you've got like, sometimes you'll see a green car, sometimes you'll see a yellow car. But how often do you encounter those? and it might just easier to be just create a category other, okay, for all of these very unusual things, and that's what this will do, right? So step other can do that, right? So we can add that as a step, and we can say take neighborhood and make an other category with threshold 0.01. Okay, so we're just adding this to our thing, and then once you do that, go ahead and make nominal predictors. Okay. This is the way the binary encodings go. Okay. Again, is you have kind of one of the categories is set as a base, and then everything else gets its own kind of gets its own thing, right? So this is kind of your how the things get encoded. So when we estimate the when we look at the summary for this, we only have coefficients for building type. There are 5 building types. We have 1-fam, 2-fam complex, duplex, townhouse, and townhouse E, or whatever. Okay, we have 5 of these things, but only 4 of them got coefficients because, again, the base level is what happens if everything else is a 0. Okay, so there's no need for that. Okay, with if you wanted to do all 5 or something, okay, you can kind of specify that in the arguments for step dummy. Okay, so you can call 1 hot or something like that. Okay. You can also add interaction terms. As far as your in base R, the way we do interactions is you would use the colon between kind of is there an interaction between building type and square footage, or you would use the star. Okay, and you do neighborhood plus this times this, and this would do it would calculate a value for square footage and a value for building type and values for the interaction. Okay, and we want to know is as the square footage increases. Okay, so it looks like according to this, right, for single family homes, as square footage increases, sale prices go up. But for whatever reason, this 2-family complex and the duplexes, it seems like even though it gets bigger, the price doesn't increase as dramatically, right? So these play a different, somehow the effect of square footage doesn't have the same effect as it does, having a bigger property doesn't necessarily increase the price over here as it does for single family homes. And so, that's an interaction effect. This is how it would be done in base R. You would use the colon or the star, and that's probably something we've seen from 101A. Okay, when you do recipes, you can add an interaction. Okay, so so again, it's kind of just like cooking. You just say, oh, add this and do this additional step. And so we're just kind of making our recipe bigger and bigger, right? And so here we're going to say, you know what, add interaction terms. That's going to be step interact. And here we're going to take the ground living area, interacting with basically anything that does that involves the building type. Okay, so now that now that we've turned building type into a nominal predictor, each of those kind of dummy variables, we want to look for interactions between each of those dummy variables. Okay. Okay. This is not going to work here. If you just take the variable and the factor, this won't work. You got to kind of turn it into dummy dummy variables first. Okay, so in our case, we for the recipe you have to make dummy variables first, and then make interaction terms for each of those dummy variables. Okay. Maybe I'm getting a tiny bit ahead of myself, but sometimes, when we started off with longitude and latitude, we just said, okay, you know what, we're going to, it's a plane, and this corner of town is cheap and this corner of town is expensive. But you might want to have some kind of different shaped surface, not just a flat surface, but something that allows for kind of like, not just this corner is expensive and this corner is cheap, but just like, maybe, there's this one segment that forms like a little hill or something like that. Okay. And so to kind of allow for these nonlinear things, is we can try using a spline function. Okay, and in ggplot we can use geom smooth, and in base R, you have functions like low s that kind of fit these smoothed out, kind of splines. Okay, or there's natural splines, and you can kind of have different. So here we have 2 spline terms and 5 spline terms, and as we add more and more spline terms, we can see there's more flexibility. Okay, and so one thing that we can do is we can take one of our, in our case, we can take the latitude variable, okay, which is basically how far north or how far south it is, and we can say, you know what, let's turn this from a direct numeric variable where we need to have this thing, but let's turn it into kind of a spline. Okay, and so here, how complicated of a spline do you want? You can kind of just ballpark here. We're going to just say, okay, let's go ahead and use 20 spline terms. It's a bit of an arbitrary choice, but again, we can add that to our recipe, and we can say step, make a natural spline out of the variable latitude. Okay. And so, this is a lot and it feels overwhelming. But again, each of these things in of themselves, these are just steps, okay, that I think we can read and understand. And this is also one nice thing about the tidyverse and Tidymodels, is that these complicated pre-processing steps processing thing is broken down into simple steps. So we provide the formula with all of the variables that we're going to use, and then we're going to perform a transform ground living area with a log transformation. We're going to group some of the categories in the neighborhood. If there's not enough represented, we're going to just throw them into an other category. Okay, we'll turn all of these things into dummy variables. And then we're going to add interaction terms between building type and ground living area. And then we want to take the variable latitude and allow for it to have, the kind of this natural spline curviness response in there. Okay. And in statistical learning with R, the other textbook that we're doing, we'll talk about natural splines, and we'll talk about regression trees, and we'll talk about some of these different kind of techniques and models that we're using, and all this is to show that with the Tidymodels, it makes a lot of these steps easy to deal with. Okay, well, all right, there's more stuff, and we're going to run out of time here, but do your textbook reading. I didn't assign chapter 8 as part of this homework, but I do recommend doing some reading of chapter 8. But yeah, and they have, like text processing things, okay? There are a bunch of different possible steps, okay? So if you just go to the reference, right? So if you go to recipes.tidymodels.org and you go to the reference section, there are a whole bunch of different steps possible, okay? So you have imputation steps, okay? So imputation is basically if an observation has a missing value, how do you fill in the missing value, right? And probably one of your most common things is just say, oh, let's take the mean of that variable and just plug it in, okay? And overall, it's not a good strategy, okay? Because that's just assuming we didn't observe this, so this is going to be average, right? And that's ignoring any kind of correlation between variables, right? So let's say you want to make a prediction on someone and they're like super tall, but for whatever reason you didn't have their like shoe size. Okay, is it if this person is super tall, are they going to have average size feet? Probably not. They'll probably be above average or something. So there's all kinds of things for how do you impute. Now if you just want to impute the mean, sure, you can do that. Okay, but if you want to impute other values, you can impute k and n and stuff like that. Okay. Transformations for individual variables, right? So we can do log transformations for any of these variables, but you can also, I don't know, harmonic transformations. I don't know. I wouldn't even know how to approach something like that, right? That's you tell me hyperbolic transformation. I'm scared already. That was like, oh gosh, just flashbacks to the hyperbolic sign and those functions and how those work. Okay. You can take a numeric variable and you can kind of break them up into chunks, right? You can cut them into factors, right? That's like what we do with your ages. Okay. So, marketing says, okay, if you're under 13 to 17, you're in this one demographic. If you're 18 to 25, this is the type of music that we're going to try to push on you. And if you're, 25 to 35, you get this, and these are the commercials, right? If you're over, 55, now we're going to show medication commercials and stuff like that. And, and basically rather than just taking your number, we're cutting them into, different groups. And, loosely we've got, Gen Z and millennials and Gen X and boomers and stuff like that, right? But that's basically taking the numeric variable age and we're cutting it, right? So these are all different kind of things. We've got dummy variables and encodings and look at all of these options you have, right? So anytime you have a pre-processing step, I would say, come to the reference and just look at some of these things that are possible, and you say, oh, maybe this is the step that I need to be doing, right? So that's your reference section, okay? And then here's just a little bit of articles. So this one is just like, how do you handle the categorical variables? And this is like creating dummy variables. And we already saw this, but this is just some more examples. And then another thing is kind of the idea of subsampling or, perhaps skipping some steps, okay? And so, for example, class imbalance and skipping steps. So sometimes this is a thing that happens in your data is, again, maybe one of the things is you're doing a financial thing and you want to predict who's going to default on their loan. So, someone borrows money and then they have to pay back a certain amount every month, but sometimes somebody doesn't pay back, right? Doesn't make their minimum payment. And we say that person has defaulted on their loan. This is a fairly rare occurrence. Most people who borrow pay back their money on time every single month. But maybe 2%, some number less than 5%, just a couple percentage of people, something happens, they don't pay it back. Okay, and if you wanted to just maximize prediction accuracy, the easiest answer is just say everybody pays back their loan. I'm 98% correct. Okay, and and you would be. Okay, but that's actually but that's not a very helpful model, right? To just say everybody pays it back, because what we wanted, it's the ones who default. That's the thing of interest, at least for the bank and stuff. And so this a little bit counterintuitive is you say, okay, well, I've got millions of observations here. Okay, let's say I've got 1,000 people, 20 of them defaulted, 980 did not. So what you can do is you can downsample. So out of your 980 that did not default, you might randomly select only 20 or 30 out of that thing, okay? And so now you have 30 people who did not default, 20 people who did default. Your data set is much, much, much smaller, but now you can try to start to pick out the differences. What's the difference between these 20 and these other, 20 or 30 people, okay? Now, that pre-processing step of reducing your training data down to this much smaller thing should only be applied to the training step. So when you do it on the test set, you want to skip that downsampling step, okay? And so so this is an article that talks about some of these ideas here, okay? It's a little bit too much to cover everything all at once, and just like all of life, only read what you really need to read. But there's lots of reading, lots of reference and resources out there available. Yeah.
For the final project,
yeah.
Until when do we have to set some kind of group for that?
Okay. Yeah. So by next week, you want to have your groups established, and you'll probably want to start meeting. So next week, I'll release the instructions and the data set, and probably 1 week from today I'll have the I hope to have the data set ready to go and the project ready to go. Okay, that's all I've got for you today. We'll go ahead and end here, and have a great weekend. We'll see you next week.